Hello everyone, my name is Amir Hossein Dadesada. I'm a PhD student at the University of Bristol alongside my collaborators Dr. Alan Woon, Dr. Michal Rolniski, and Professor Majid Mirmehdi. Today, I'll be presenting our work exploring motion boundaries in an end-to-end network for vision-based Parkinson's severity assessment. So let's start. I have divided my presentation into 5 parts. First, I will start with introduction, then we'll talk about the related works, then I will explain our method, how it was developed. After that, I will show you our experiments and results, and I will finally finish my presentation with the conclusions and our future work. Okay, let me start by discussing about the motivation which gives us an answer to the question why Parkinson's disease severity assessment is very important. Parkinson's disease is the second most common neurodegenerative disorder after Alzheimer's, which affects about 1% of the world population over the age of 55. As you can see, the right-hand figure here shows that the death rate from this disease in the US has gradually increased over the last decade. In this slide, you can see the main symptoms of Parkinson's disease, including tremor, slow movement, stiff and inflexible muscles, and postural instability. These symptoms actually affect patients in performing everyday tasks and impact the quality of their life. Unfortunately, there is currently no cure for Parkinson's disease. However, regular clinical assessment of the symptoms of this disease are required to tailor symptomatic treatments and optimize disease control. And this can be very crucial in the trials of any drugs. Assessment of Parkinson's disease is normally performed in clinical settings, in which the patient is asked to perform a series of physical tasks while being assessed by a trained nurse who makes an evaluation and assigns a score. However, such process of assessment is highly subjective and also needs an available rater. So automating Parkinson's disease assessment can be very helpful to eliminate these limitations. That's why our main interest of this study is to develop an end-to-end machine learning-based method that allows us to evaluate the severity of Parkinson's disease from only video data. Before going into more details about our approach, I will briefly explain the related works in Parkinson's disease severity prediction task. Recently, challenges in Parkinson's disease have been addressed through machine learning techniques. Most of these methods are based on force sensors, wearables, and other on-body sensors. Researchers normally use the signal come from the sensors as the input of their machine learning-based algorithms. However, the use of these sensors have many limitations because they are mostly inconvenient and sometimes very difficult to attach to patients. Some researchers also focus on depth-based sensors like Microsoft Kinect to capture data from patients. Although using depth-based cameras are more user-friendly than wearable sensors, they might not be suitable for all environments, and they will increase the computation cost as well. There are also a few works which they only used RGB data for this task, and most of them are rely on handcraft feature extraction and pre-processing steps, which may limit their model's representational capability. However, as I mentioned before, we are interested in assessing Parkinson's disease severity with only RGB data in an end-to-end network without the need for any pre-processing step and handcraft features. The Parkinson's disease dataset used in this study is collected at North Bristol Trust in Bristol, UK. This dataset contains video data from 25 patients between the ages of 41 to 72 years. In this dataset, we have 1,058 videos spanning two different tasks, including hand movement and gait. In the first task, as you can see, the patients had to open and close their hand 10 times as fully and as quickly as possible. The second task is gait analysis, in which the patients walk 10 meters at a comfortable pace and then return to their starting point. In this slide, I'm going to show you some video samples of our dataset in different severity level. As you can see, in the first row, the patient can perform the task very well without any problems. And this is an example of a normal subject in our dataset who are at very early stage of Parkinson's disease. However, in the second row, the patient can barely perform the task. And this is an example of a severe subject in our dataset. In this part, I'm going to explain our proposed approach in more detail. As I mentioned before, the main interest of this study is developing an end-to-end network to evaluate the severity of Parkinson's disease without any pre-processing steps. That's why we went through the recent advances from deep learning techniques in human action recognition to find a practical design choice for this task. We also used an extra input modality called motion boundary to suppress the influence of camera motion, which is very common in real-world video data. We used motion boundary along with other input modalities like RGB and optical flow in a multi-stream deep learning configuration to improve the performance of our model. Now I will briefly explain our network architecture. Here we used I3D-CNN as the backbone of our deep model to directly learn spatial and temporal features from video input at a low computational cost. This I3D is a kind of 3D CNN that inflates all the 2D convolution layers into 3D convolutions. This strategy actually made this network a deep 3D CNN with many fewer parameters. We trained this I3D network with a sparse temporal sampling strategy. This training strategy helps our network to model long-range temporal structure in the patient's action. We found this strategy very efficient to analyze the complex motions of our video data, which are relatively long. Inspired by the success of attention mechanism in human action recognition, we also applied attention units along the temporal axis to assign individual attention weights over each feature vector. This mechanism enables a more reliable model because it allows our network to focus more heavily on the important segments of a video which may contain absolute classification information. This is motivated by the fact that in some cases, clinicians are able to pass judgments on a patient based on moment reactions, for example, an interruption or hesitation during the hand movement task. In this figure, you can see the architecture of our proposed method. The whole model can be trained in an end-to-end manner by only one loss function. First, we extract spatial and temporal features from K video snippets using a single I3D network. This network actually shares all of its weights with the other branches. Then, the spatial and temporal features of the last convolution layer for each video snippet fit into an attention unit. This unit consists of two fully connected layers by a ReLOOK activation function and a sigmoid function to generate attention weights between 0 and 1 for each video snippet. So, by this technique, we weight each feature vector by its corresponding attention weight before being forwarded to the consensus function. Finally, we use a softmax layer to output class score predictions. Please note at every training and testing process, the network takes one input modality amongst RGB, optical flow, and motion boundaries. So we only processed one modality at a time. Here you can see our motion boundary computation from optical flow components. As you can see, for each flow component, we compute two motion boundaries via derivatives for the horizontal and vertical flow components. Then the final motion boundaries are obtained by their sum. It is clear that optical flow contains constant motion in the background, which is removed after computing motion boundaries. In this project, we also needed to deal with class imbalance problem. For example, in the Parkinson dataset used in this work, the number of videos belonging to the scores 3 and 4 is significantly lower than those belonging to the other classes. Therefore, we have a class imbalance problem, which can lead to a model bias towards the classes with large number of samples. In order to mitigate this problem, we applied two strategies. In the first one, we grouped the scores into three classes. Score 0 for normal subjects, for example, patients who are at very early stage of Parkinson's disease. Scores 1 and 2 for subjects with mild symptoms, and scores 3 and 4 for subjects with severe symptoms. In the second strategy, we utilized focal loss to train our multi-class classification task. This focal loss actually helps us to downweight easy classes and better weight rarer classes by adding a factor to the standard cross-entropy loss. In this part, first I'm going to show you the impact of different input modalities in our multi-stream configuration. Then I will show you the effect of our attention mechanism and also the performance of other deep architectures on our both Parkinson's disease tasks. You will also see the effect of focal loss on the performance of our model. Here you can see an overview of our multi-stream configuration. We used such configuration to combine the predicted scores of our model with different input modality. We actually trained our model with each different input modality separately and then used a late fusion approach at test time to average over all predicted scores. The results in this table show comparative evaluations on different input modalities. For the hand movement task, motion boundaries alone perform best. However, for the gait tasks where there is much more dynamic movement, all modalities perform comparatively well. But as you can see in the table, in this task our model with flow and motion boundaries achieves the best performance. On average, the use of motion boundaries is promising as a significant extra modality because it can contribute to improved results. To evaluate the influence of the attention units, we perform all our experiments with and without them. As you can see in this table, in all experiments for hand movement and gait tasks, our model achieves better accuracy with the attention units. Interestingly, even without attention units, motion boundaries play a significant role in improving their results over other modalities. This table provides the performance of other deep architectures on our Parkinson's disease task for both hand movement and gait. All the network weights were initialized with pre-trained models from kinetics dataset, except for the slow-fast network, as one of the properties of this model is training from scratch without needing any pre-training. Although we examine the performance of these architectures for all possible input modalities. We only report here their best results. So, for example, for I3D, its best result is when using flow and motion boundaries. As shown in the table, our proposed approach performs better than these popular networks for both hand movement and gait tasks. In this table, you can also see the importance of using our focal loss, in which it provides a better accuracy on both tasks. To sum up, we propose an end-to-end network for the assessment of Parkinson's disease severity from videos for hand movement and gait. Our model is based on an inflated 3D scene and trained by a temporal sampling strategy to exploit long-range temporal structure at low cost. We also applied an attention mechanism along the temporal axis to provide learned attention weights for each video segment, allowing our model to focus more on the relevant parts of each video. We showed that this technique increased the performance of our model. We also proposed the use of motion boundaries as an extra input modality to suppress constant camera motion, and we showed its positive effect on the accuracy of our model on both Parkinson's disease tasks. A main limitation of our method is that it's unable to handle several Parkinson's disease tasks in one training process. To address this problem, as our future work, we are going to use unsupervised learning and adopt multiple loss functions with an effective way to combine them. Thank you for your attention.